I'm Tom Goodwin, and I will be presenting my thesis research on the characterization and performance of robust membranes infused with perfluoropolyether oils for water purification. I did this research in Jessica Schiffman's lab in the Chemical Engineering Department with graduate student mentor Rushab Shah. 1 in 3 people lack clean drinking water access today in the world. That leads to over 2,000 deaths every day from unsanitary water. So there's a clear need for water purification. Now, one of the most common methods of water purification is ultrafiltration, which uses membranes with a pore size of roughly 5 to 100 nanometers. Now, these small pores restrict large particles from passing through, like pathogens, whereas water molecules are small enough to pass through the pores. And this is depicted in the diagram above. However, one of the biggest problems with ultrafiltration is fouling. Fouling is the accumulation or binding of particles at the surface or in the pores of a membrane. And so we can see in the diagram that all of these particles are preventing anything from passing through the membrane, which significantly decreases filtration efficiency. Some examples of foulants are bacteria, viruses, proteins, and just any large particles that are, or large impurities like dust. Now, our lab uses this novel method, liquid-infused membranes, to prevent fouling. This is bio-inspired by the pitcher plant. The pitcher plant secretes a lubricant to its surface so that when insects crawl in it, they slip off into its mouth. So we're kind of mimicking this with our rough membrane surfaces that are polyvinylidene difluoride, and we're lubricating them with these perfluoropolyether oils. And so the idea behind this is that since they both have similar fluorine chemistry, the surface energy between the interface is very low. And so the oil will wick across the surface of the membrane and fill in all the rough spots. And we can see that in the diagram above, going from a porous surface to a lubricated surface. Now, the diagram on the bottom right just shows how we actually fabricate these liquid-infused membranes. Now, something we want to keep in mind is this emerging concern for per and polyfluoroalkyl substances. In fact, last month, the EPA actually announced a new national drinking water standard for PFAS. The reason for concern is that these chemicals cannot really be metabolically broken down, so they get this forever chemicals nickname. And this leads them to bioaccumulate in living organisms. Now, some health concerns associated with these compounds is increased cholesterol levels, hormone interference, and they may even be carcinogenic. Now, it's not totally understood which PFAS are dangerous. However, these are just a few on the right that were included in the EPA standards. And it's also not totally understood why they're dangerous. So while our oils are considered safe that we're using on these membranes, we want to make sure that they're not degrading into any harmful substances and we're not going to further contaminate drinking water. So now just to loop back to our liquid-infused membranes, we want to characterize these once we fabricate them and make sure that they are stable and slippery. So to do that, we use a crystal violet stain test. This involves taking our sample, putting it in a crystal violet dye on a shaker plate for 15 minutes and letting it soak. Now the bare membrane is hydrophilic, so the dye will stain it, whereas the oils that we use are hydrophobic, and so the dye doesn't interact with them at all and doesn't stain. And we can see in the pictures up top that the bare membrane almost completely stains purple, whereas the liquid-infused membranes have little to no staining. This means that there is a continuous, stable liquid surface being formed on our membranes. And we can further confirm this with our SEM images below. The picture on the left shows the bare membrane SEM image, and the two on the right, we can actually see that bare membrane has liquid coating all over it. So now, now that we know that we have stable liquid-infused membranes, we want to learn more about their filtration properties. And so to do this, we flow pure water through our limbs in a dead-end filtration system that's pressure-driven. And so we do 15 minutes of free flow to allow steady state to be established. And then we measure the flux for 15 minutes. And from these flux measurements, we can actually calculate permeance, which is shown in the graph on the right. Now we used limbs fabricated from 0.1, 0.22, and 0.45 pore size membranes. And we also performed for each of these membranes 1, 2, 3, and 4 bar applied pressures for our filtration. Now, we also normalized, I should note, we normalized the permeance to each of the bare membranes so we can actually compare between the different pore sizes. And so we can see for the 0.1 and for the 0.22 that while there is slight changes between the different pressures, none of them are statistically significant. Whereas for the 0.45, there's large changes between each of the pressures, and they are all statistically significant with a p-value of less than 0.05. And so this kind of lets us infer that pore size does affect how the oil behaves on membranes, and also does affect the filtration properties at different pressures. So now that we know this, we also want to learn more about how these liquid infused membranes perform over time. And so to do this, we perform basically the same exact experiments, except instead of changing the pressure, we keep it constant at 1.5 bar, and we just perform repeat cycles for each of our samples, 5 specifically. And so we did this again for 0.1, 0.22, and 0.45 pore size membranes. And we can see for each of these that there is no significant difference in permeance between each of the cycles. However, we can, if we look at cycle 1 on the graph, all the permeance values for each of the membranes are slightly lower. And so this may be attributed to some slight oil loss during the beginning of the process. However, overall, we do want to confirm, or we want to say that the filtration properties are almost constant, which are very good. Now, considering this oil loss, we want to keep in mind the dangers of PFAS that we were talking about earlier. And so one of the chemicals used in industry commonly to clean membranes is bleach. So we took our oils and we soaked them in bleach for 1, 2, 4, 8, and 12 weeks. We then took these samples and performed thermogravimetric analysis on them, or TGA. The idea here is that if the PFAS, or if our oils degrade at all, there's going to be a lower molecular weight distribution. And if this distribution changes, then the TGA profile will also change. We can see in the graph on the right that for all the different samples, the TGA profile looks almost identical. So there's no evidence that the molecular weight is, or that the oils are degrading from this data. However, we do need more characterization to confirm this. So to just summarize everything I went through, liquid infused membranes were fabricated and are stable and slippery. The limbs permeance versus pressure relationship changes with pore size, which tells us a little bit about the mechanism of the oil in the pores. Limbs permeance is stable with repeated cycles of pure water, which is good for long-term performance. And also, there is no sign of oil degradation from just our TGA data. So for the next steps of this project, we want to quantify oil in the permeate, and we'll do this by using total organic carbon measurements on all the samples that we, or all samples of permeate that for the experiment I described. We also want to characterize the oil degradation by using NMR, and so this will more directly measure the molecular weight of the oil and determine if bleach degrades these oils. So lastly, I just want to thank my committee chair, Jessica Schiffman, my committee member, Todd Emmerich, my graduate student mentor, Rushab Shah, and my undergrad lab mate, Oshio, as well as the Schiffman lab. I couldn't have done any of this research without them. And that being said, thank you for listening to my presentation.